and welcome to a new topic under this remote sensing essentials course. And today we are going to discuss about image characteristics, especially we are talking about digital images which we will be using, or remote sensing or satellite based images, and different resolutions in remote sensing. In earlier discussions sometimes we have touched resolutions, but not all and not as per the in detail or in definitions. So, today we will be looking definitions of different resolutions. There are 4 in remote sensing. So, all this we will be discussing. So, let us start. As you know that it is a very famous phrase that a picture tells 1,000 words, and I have added one more line in this one, and that means the satellite image tells 10,000 words. Because as in the earlier part of this course we have discussed that remote sensing images are digital and spatial and generic. And generic here that means that these images can be used for various purposes. Some people might be using for weather forecasting, some people might be using to cover vegetation or vegetation index, maybe some people using for snow cover mapping, some people are using for civil engineering, geologist might be using to find water resources or oil or some mineral resources. So, different people uses different. There are various applications. A single image can be used for 10 types or more than 10 types of applications. So, that is why a picture tells 1,000 words, whereas a satellite image tells 10,000 words. We will be learning also during this course that how we can exploit the capabilities of satellite images for our own benefits and applications. So, what exactly an image is? Earlier also we have a little touched about this part, but today we are going to discuss in detail about what is exactly an image. When we say an image, so an image is basically a pictorial representation of an object or a scene, and there are various forms of images. As you know, the analog images is a very common form, used to be. Now we are also having a digital form, which is what we get from satellite images. Nowadays also digital cameras, maybe SLR camera or maybe a camera inside a mobile. So, these are also digital images, but they are in form of snapshots. So, that we will also discuss the difference between an image taken by a satellite sensor and an image taken by your mobile or digital camera. The analog image is basically produced by photographic sensors on paper based media or a transparent media. So, that way we call as a analog images. Earlier when we did not have these digital cameras, we used to have exposures of a scene on a film, and usually it used to be negative, and then a positive print used to be printed out of that negative. So, those are the analog images. Aerial photographs also, which are in many countries these are used because lot of security issues. In India now we do not acquire latest aerial photographs, but old aerial photographs can be found of India. They are all analog images that they have been taken by a photographic sensor or a camera using a film, and that is how these analog images are generated. There are variations in scene characteristics which are represented as variations in basically brightness, and generally the aerial photograph which we used to use were in the black and white or in shades of grey. So, that is also a very common thing, but later on also colored aerial photographs were also available, but all those have been taken by a photographic camera on a film itself. And the basis basically here is the same as in case of satellite images, that objects reflecting more energy appear brighter on the image or on a photograph, and objects reflecting less energy appear darker, and objects which do not reflect any energy, they appear almost black on a gray image or gray photograph. What exactly digital photograph? Which is produced by electro-optical sensors. So, whether it is on board of a satellite or handheld, maybe in mobile or a digital camera, these are produced by electro-optical sensors. Also in later part of, or in the next discussion, we will be looking how exactly these images are created by onboard satellites sensors. So, that part we will be also discussing. Now, if we go more detail about this that a digital image produced by electro-optical sensors, which is composed of tiny equal sized square picture elements, also we call as pixels, which are arranged in a two-dimensional matrix. This is what in a two-dimensional array is used in a typical digital camera, and with each pixel is associated with a known number as a digital number or DN or pixel value or brightness value, or when we talk in terms of grayscales, then gray value, which is record of variation in radiant energy in discrete form. So, what these opto-electro sensors are doing, optical sensors are doing, they are basically recording this brightness or reflection which is coming, or maybe the radiant energy, maybe the thermal one also, which is recorded by these sensors. And again the same thing like in case of a photograph, analog one, that an object reflecting more energy records a higher number for itself on the digital image, and vice versa is also true. That means an object which is reflecting very less energy will be recorded with a less value. So, if I talk in terms of say if I take an example of 8-bit image, and that too just 8-bit image, and the values are might vary between 0 to 255. So, the objects which are reflecting no energy or almost very little energy may have the pixel value near 0. And the for example, maybe an infrared channel, a water body, a pure water body will completely absorb the infrared energy, and therefore, there will not be any reflection, and therefore, the water bodies may appear completely dark, or pixel values of these water bodies might be near 0 or maybe even 0. The same way with the pixel which are recording high pixel value might be coming from like a fresh snow surface, which will have a very high albedo and might be recording pixel value near 255. So, in that way this is how these digital images are created. Of course, when we combine 3 images, then we achieve the color, which we will be discussing also later about that. So, an image is basically a raster data, which is a 2-dimensional matrix in mathematical domain, and that each unit of the unit of this matrix is a pixel, and which is square in shape. However, overall shape of a raster data or a 2-dimensional matrix can be a square or rectangular, but the unit will always be having a square in shape. That is, in our case in digital image, that is the unit is pixel. And this I have already mentioned that overall image can be either square or rectangular in shape, but unit has to be always in square. This is the limitations, or you can say the advantages with raster, that each unit will have the same size and same shape, and the shape is square in shape. One example is here that if we blow this gray image here, what we see, if we blow this image, then what this is how we see, except these black lines which are showing individual pixels, that grid is not really there, it is just used to demonstrate this thing. So basically this is an example of 8-bit image, and therefore you can see there are values which are having pixel values which are 0, and that means no reflection is coming at all if it is visible or infrared, and there are some pixel values are also showing 255. So rest are in between. So this is a typical example of a 8-bit digital image. Now when we discuss all this, we also use some terms which I will explain here. So we say number of rows and number of columns. So these are the rows which runs in horizontal direction, and these are the columns which run in the vertical direction. Generally, when image in geometric domain, the origin is always considered from top left, but when image is having the geographic coordinates, which we will be discussing under a new topic, which is georeferencing of satellite images, then once an image is georeferenced, that means it is now having geographic coordinates, then the origin would be shifted to bottom left. So normally when image is acquired by the satellite, the origin is always referred from top left. Like for example, if I have to refer this pixel, then I would say column second, row 2 also. Likewise, I will address that one. But once I am having geographic coordinates, then origin would be from the bottom left. Now the pixel value which one is the pixel, that is the location, then next is the value. So the pixel value, that is the magnitude of electromagnetic energy captured in a digital image, which is represented by positive number, digital number, and these are positive integer values. You can see here also in this example that all values are positive integer values. There are no decimals, there are no floating points or real numbers, and there are no positive or negative signs. So when there is no signs, we consider as a positive, and these are all integer values. So whole number. So all images which you see, whether taken by a satellite sensor or by digital camera or maybe your mobile camera, if you start seeing using some software the pixel values, you would find that they are always positive integer value, whole number. So these numbers are in form of binary digits or bits say, and may vary between 0 and a selected power of 2. So if it is 8-bit, then 2 power 8, and if it is 7-bit, then 2 power 7. Likewise, these are captured by the different sensors. Each bit records an exponent of power 2. For example, 1 bit is 2 power 1 equal to 2. That means binary image, and the pixel values can vary between 0 and 1. Total variations would be 2. Similarly, maximum number of brightness levels available depends on the number of bits used in representing energy recorded. If I take example of 8-bit or a byte image, 8 bits image, that means 2 power 8, that would we will be having total number of variations or total number of values we can have, varied values, that is total 256 between 0 and 255. So 0 is also counted here, that is why the total is 256. And this is the 8-bit image is the most common image, and also most of the softwares about digital image processing or photo editing softwares are very much capable of handling 8-bit images very easily. If you combine 3 bands, create a colored image, then it becomes 24-bit, still these softwares can handle. So this 8-bit combination is the best suited for, and many satellite sensors also acquire these images. So this is a sort of summary that, as I have mentioned, that if it is 1-bit image, that is binary image, total variations you can have 2, and the color levels, either it can be, the pixel value can be either 0 or 1. If I take example of 7 bits, then 2 power 7, total number of variations is 128, values varying between 0 to 127. Similarly, if I go for 16-bit image, 2 power 16, so this is 65,536. So, lot of variations would be available, but always one has to keep in mind there is the storage requirements. Higher the bit of an image, that means the depth of a pixel can have, more space it would require, and this is sort of the space requirement is exponential. So, that you can imagine that if I take a 24 bits image, then it is 1.67 million colors or variations of pixels I can have, because now 3 bands of 8 bit each have been joined here. So, then space requirements would be more than 3 times. Let me take some example of course, these are not basically acquired by the satellite as it is, but these have been deteriorated just to demonstrate to you. So, the original image is 8-bit image, then it has been deteriorated to 4 bits, further to 2 bits and then binary. And as you can see that in binary image in the left side example, that you are having only 2 values, either black or white, no other values are there. Whereas in case of 2-bit image, as you can see here, that the maximum variations you can have 4, and therefore few gray values are also possible. This is what you are seeing. So, you are seeing black, very dark gray, light gray and white. So, the variations are like this only. When we go for 8 bits, of course, total number of variations an image can have in terms of pixel values 256, and therefore, the appearance of that image compared to 1 bit, 2 bit and 4 bit is much better. So, higher the bit is, higher the variations an image can have, even if it is black and white, it will appear much better. But here keep in mind that there is no change in the spatial resolution. Spatial resolution remains same in the all 4 examples, only this quantization or radiometric resolution, which we will be of course discussing later also, has changed. So, 8-bit image just for demonstration has been deteriorated to 4 bits, 2 bits and 1 bit, and you know that what happens to the quality. So, these are the advantages, but 8-bit is most common one. When we go for colored images, then you use this color space and a additive color scheme, where there are 3 primary colors, blue, green and red, BGR or RGB, whatever the way you would like. Here is the example that visible part of EM spectrum, one image of green part, then red part and near infrared part. Why near infrared part? Because this image target here is creating a false color composite. So, I can discriminate vegetation much easily. And as you know that when we were spectral curve responses, we saw that vegetation having high reflectance in the infrared part of EM spectrum. So, this channel has also been used and assigned red color, whereas red channel of visible part of EM spectrum has been assigned green color, and the first one, the green, has been assigned blue color. Now, when we combine using this additive color scheme, then what we get a false color composite. Why false color? This I also earlier mentioned, but today also I will explain to you that false color, because vegetation is not appearing as green. This is what normally we expect, but why it is not appearing green? It is just explained to you that infrared channel, which is having high reflectance in infrared part of EM spectrum, has been assigned red color. Now, there can be a question that why we are assigning red color, instead red channel should have been assigned red color and green channel should have been assigned, then we will end up with the blue. One can create that combination, but there are some standards have been made when we started using remote sensing since 1972. When we say standard false color composite, that always means that infrared channel has been assigned red color, and therefore, we use this kind of combination to create false color composites. And everyone understand, once I say false color composite, that means infrared channel has been assigned red color. The purpose here is to discriminate objects, to depict different objects, identify different objects very easily by using this color combination. But this is, each image here is 8-bit. Now, when we combine, then this false color composite would be 24 bits, that is 1.67 million colors it can have, variations in colors it can have, because now 3 colors have been combined. So, this one has to remember. Now, as you know that normally single channel data is only used in panchromatic camera, which many satellites are having, like we started our own Indian panchromatic camera. We started with the IRS 1A, 1B and IRS 1C and 1D, and so on we started, and then Cartosat and Resourcet, all these are having panchromatic camera, not in one IRS 1A, 1B. Same with the pan camera, also started with the spot also. So, and but the same time we also had multispectral images. So, pan cameras were also used, and same time multispectral sensors. That means data is being gathered for different part of EM spectrum. Here is the example: band 1, band 2, band 3 and band 4 are representing different part of EM spectrum. This is an example of our own IRS 1B, list 2 was the sensor, IRS 1B was the name of the satellite. And this is part of foothills of Himalaya, or part of Himalaya is also there, the Ponta Sahib. So, what we see, the band 1 is 0.45 to 0.52, and similarly next band starts from 5.2 to 5.9, then 6.2 there is some gap, and then this. So, we can use these channels. As you can see that this infrared, the band 4 is showing altogether different characteristics of vegetation, whereas all in these 1, 2, 3 the vegetation is appearing red. So, if I combined by assigning red color to band 4 and then blue and green to either these 3 bands, then I get a false color composite image. So, this is how a false color composite image can be made, by choosing 3 bands which are having maximum variation present within them. Of course, infrared, in a standard false color composite, infrared channel is always assigned red color. Now, resolutions. There are 4 types of resolutions which we discuss in remote sensing, which are used in remote sensing. So, first we take as a spatial resolution. A spatial resolution, that is the ability to distinguish closed space objects on an image. That can be the, if you search the net or maybe some books, you would find little more complicated definitions of resolution, but this is the most brief and very appropriate definition: ability to distinguish closed space objects on an image. So, the purpose here is that how or in other terms we say quality of image. When we are having a poor quality image, then it becomes difficult to distinguish different objects present in the image. But if I say I am having a quality image, that means each and every object I am able to distinguish very easily, and especially which are closely spaced. So, 2 adjacent objects, if they are having different characteristics, reflection or emission characteristics, I should be able to distinguish as easily as possible. And if I say that, if I find this situation, then I say spatial resolution is high. But spatial resolution is also defined in terms of the area it is covered in a pixel. So, for example, a sensor, if it is covering 10 meter by 10 meter area compared to a sensor which is covering 1 meter by 1 meter area, to create 1 pixel in an image, then 1 meter is having higher spatial resolution. And whenever we say higher spatial resolution, lower spatial resolution or coarse spatial resolution, it is always relative terms. If you recall the brief discussion we had on NOAA AVHRR data, when this AVHRR sensor was developed, and its full form is Advanced Very High Resolution Radiometer. And now see, 1.1 kilometer in today's reference cannot be very high resolution radiometer, but at that time in 60s definitely that was very high resolution. So the high resolution few years back which we used to say for 20 meter or 10 meter is no more high. Now we talk in centimeters. So this is always talked, spatial resolution is always talked in terms of relative terms, one, and also you can compare with the size of the pixel which is representing the ground. So if a pixel is representing 10 by 10 100 square meter area, and another pixel is of another sensor is representing 1 square meter area, that means 1 square meter area is having high spatial resolution, because it will fit very well in this definition. In 1 meter resolution image, I would be able to distinguish close space objects very easily as compared to in 10 meter. Now there is another resolution which is called spectral resolution, and a spectral resolution, that is basically the location, width and sensitivity of chosen this wavelength bands. Basically the width of a band, narrow the band, higher the spectral resolution, broader the band, lower the spectral resolution. For example, generally panchromatic bands, panchromatic sensors cover a large part of EM spectrum compared to bands like infrared or near infrared or other parts. So then we say that in that sense that spectral resolution of panchromatic sensor is relatively coarser or poor because the width is much more. In case of hyperspectral remote sensing or hyperspectral images, the spectral resolution is very high because the bandwidth of individual bands might be 1 nanometer or 0.01 nanometer, 0.01 micrometer or that kind of thing. So very narrow bands when you are handling within the same part of EM spectrum, then we say hyperspectral. But generally what we are handling images are in that example, that like in Landsat we had 0.4 to 0.5, 0.5 to 0.6 and so on. So there we had the difference of 0.1 micrometer. So bandwidth was like that. Later on those have been shifted, so location has been changed and the sensitivity also in the band also. Now the third resolution which we talk is the temporal resolution. That is the repeative coverage, how frequently a satellite is covering the same area. Now this is the or also we can say time difference between observations. There is a relationship with higher spatial resolution, inverse relationship, and temporal resolution. For example, a sensor which is having high spatial resolution may have repeativity or temporal resolution very poor, because high spatial resolution images will have a very narrow swath, and that means in order to revisit the same area it may require even 28 days or so. Whereas a relatively coarser resolution sensor like NOAA AVHRR, which is having 1.1 kilometer spatial resolution, it is having very wide swath, about 100 kilometer, and therefore the revisit is 2 times in a day. 2 times in a day, daytime, and 2 times in the night time. So 4 times in a day it can revisit almost the same area. So higher the spatial resolution, lower the temporal resolution, and vice versa is also true. The fourth and last resolution which we discuss in remote sensing is the radiometric resolution, which we have earlier little touched upon. Basically the number of bits which are used to store the information about an image or a band. So, if it is 2 bits or 6 bits image and it is a 8 bit image, definitely 8 bit image is having more better radiometric resolution than a 6 bit. So, here higher the number of bits which are used to store a pixel value, higher the radiometric resolution. And this is basically, we can also say, the precision of observation, not accuracy. Accuracy and precision are two different terms. So, this one has to remember, accuracy is a statistical term, whereas precision based on the instruments which are used here. Or in this particular case, precision here, it means how precisely you are recording the pixel values. 6 bits compared to 8 bit, definitely 8 bit is having higher precision and higher radiometric resolution. So, this is how 4 resolutions are discussed in remote sensing. In day-to-day discussions also, in future lectures also, I would be mentioning these resolutions on different occasions. So, this is for that purpose. Now, we come to the this also spatial resolution. In somewhere we can also say as a resolving power of certain objects within a pixel. As you know that pixel represents an aerial average of, if I talk in terms of reflection, then whatever the reflection or variations which were present within one pixel of ground, equivalent to ground, all have been averaged down and one single pixel value has been assigned to a pixel of an image. So, in remote sensing, the resolution or spatial resolution means here the resolving power, which is capability to identify the presence of 2 objects. Now, sometimes 2 objects, the image might be a coarser resolution image, but 2 objects, if 2 adjacent objects are having very contrasting characteristics, still these can be identified. So, one has to also take from that that direction, and I will give you example. When we started using Landsat MSS data, at that time the spatial resolution was around 80 meter, but still we were able to distinguish a single railway track, and as you know the single railway track is not 80 meter wide, it is hardly 2 or 3 meter total. Total is hardly 2 or 3 meter, 2 meter wide. And because not only the distance between 2 rails, but also in the surrounding. The reason was why we were able to distinguish railway lines, because one, they were having contrasting characteristics than the surrounding, and these were the linear. So, if objects are like that, though maybe smaller than the spatial resolution, but if they are having contrasting surroundings, still these objects of smaller size can be identified. So, 2 adjacent objects, if they are having contrasting surroundings, they can be identified even a relatively coarser resolution images. Capabilities to identify the properties of 2 objects, properties here the reflection, emission and other things, and then we can drive other parameters out of these basic values or brightness values. So, an image that shows finer details is said to be a finer resolution compared to the image that shows coarser details. So, when we say I am having high quality of an image, that means I am talking about fine resolution. The size, pixel size is very small, representing a very small part of the earth, 1 meter compared to 100 meters. So, 100 meter is always a coarse in relative terms than compared to 1 meter. Some examples are here, like 1 meter resolution image, 2 meter resolution, 4 meter and 8 meter. As you can realize, again these have been generated for demonstration. So, the image quality has been deteriorated, so that we can realize that if a sensor is acquiring an image of the same area at 8 meter resolution, this is how it will look. And when it is the same sensor is acquiring as 1 meter, this is, as you can see, that 1 meter image resolution image is showing much more details as compared to 8 meter. In 8 meter image, in this example, hardly you can distinguish anything. Even on 4 meter resolution you cannot, but on 2 meter, yes, you start distinguishing things very quite easily, and in 1 meter of course in much easier way. Similarly, here this is 10 meter pixel resolution, this is 30 meter, and this is 80 meter. As you can see that 10 meter, because this is finer resolution, the image quality is better, and therefore I can identify different objects much easily. The top example is in black and white or in gray, and the bottom example is in false color composite. So, you can identify very easily. So, higher spatial resolution is always better for certain types of applications, not all types of applications, because the basic the advantage of remote sensing was that it provides the synoptic view. That means it covers, and a single image covers a very large area, and a very large area can be assessed, seen, and interpreted, analyzed in one go. But when we go for high spatial resolution images, then this synoptic view is getting reduced, and we are going narrower and narrower. In case of hyperspectral images, maybe a 5 kilometer strip is being assessed. So, you cannot see a synoptic view. So, high spatial resolution in some way is going against the original philosophy of remote sensing, that is synoptic view. But nonetheless, there are different requirements for different purposes, for different applications. Higher and higher spatial and spectral resolution images are being used or are being acquired. So, this further on this spatial resolution, that the size of the smallest dimension on the earth's surface over which an independent measurement can be made by the sensor, that also indicates about the spatial resolution. And this size is of the pixel, which is equivalent to the ground size in meters, controlled by instantaneous field of view, that is IFOV. So, here IFOV is, that means that if it is narrow, it is very narrow, this solid angle, then your pixel is going to be higher spatial resolution. But if this IFOV is large, then you are going to have a coarser resolution. So, example is given here. This angle, this IFOV in this case is smaller, and I am getting a high spatial resolution image, whereas in this case IFOV is larger and I am getting a coarser resolution image. Here it is also demonstrated, when you are going for relatively coarser resolution images, then the nadir, when the sensor is directly looking downward, it acquires a perfectly squared area representation in a pixel, whereas in case of oblique direction or when you are having IFOV oblique due to the curvature of the earth, as you can see here, then this is though the recording is in the square shaped pixel, but the area of the ground which is it is being covered is not really square or rectangular, but it is a parallelogram kind of situation. So, IFOV also equally matters as a spatial resolution, but both are linked together. So, IFOV is the angular cone of visibility of the sensor, that is a solid angle, determines area seen from a given altitude at a given time, like here it is shown, and the area viewed in IFOV as at the altitude also, and the known as ground IFOV is also known as ground resolution cell GRC or element GRE. So, all this is there. As you can see that you are having this B area, also you are having the C area, and the A is the sensor here. So, likewise it is. Now, spatial resolution again, it is linked with larger the IFOV, coarser the spatial resolution you would have. It is a very popular figure in many remote sensing books or literature, which illustrates the geometrical instantaneous field of view reconstruction by projection from a pixel or on an image plane, as you can see here. So, this is, but remember IFOV is a solid angle. Now, so finally, we can put in proper words about the space, that is spectral resolution. That spectral resolution of a sensor refers to the number or location of spectral bands the sensor collects data in and how wide those bands are. Narrower, remember, narrower the band, higher the spectral resolution, and broader the band, wider the band, lower the spectral resolution. Whereas in case of spatial resolution, smaller the size of the pixel, that means in terms of area, higher the spatial resolution. And here also, smaller the bandwidth, higher the spectral resolution. So, a good analogy may be that how many crayons are in your coloring box? Do you have 8 or 64 colors? So, if you are having 64, that means you are having high spectral resolution. You would have variations of individual colors like green crayons. So, you may have many greens starting from lighter to darker. But if you are having just 8 crayon, you would have just one single green. So, this is how the analogy can be given. Also, spectral resolution you can see in this comparison, that in the visible part there are many channels are there of Landsat MSS, TM, ETM and Landsat OLI series, and this is what you see that MSS had relatively, though they were continuous bands and relatively broader bands were there. Just compare say band 1 here and band 1 correspond to Landsat TM is band 2, in ETM again band 2, ETM plus, and then OLI 3. So, likewise you get all these bands which are little broader. Compare this band 4, in here this is little broader, but it is becoming narrower in OLI series. So, that means we can say in OLI series of or Landsat 8 OLI, we can say the bands are having higher spectral resolution compared to Landsat 1 MSS sensor. So, narrower the band, higher the spectral resolution. I gave also example of panchromatic. Panchromatic covers a very wide band, and therefore, it is spectral resolution of panchromatic sensor is very broad or very coarse if we compare with the multispectral like this is Landsat or WorldView or other sensors are there. So, even within, if I bring this one just project here, then within one panchromatic band there are 3 bands in Landsat in multispectral scanner, and therefore, it is having higher spectral resolution compared to panchromatic. So, narrower the bandwidth, higher the spectral resolution. In hyperspectral sensors, there will be maybe 250 channels, 255 channels, and continuous channels are there. So, hundreds of channels provide a near continuous reading of optical spectrum. For example, the sensor very famous hyperspectral sensor is Everest, which was developed in somewhere in 1993-94. Initially it was on airborne, later on also on the satellites also. So, it is having continuous band, one band ends, another starts, and even it is having nanometer width compared to micrometer in case of multispectral or panchromatic. So, number of channels are more in that case. Now, we just will be doing this comparison broadband and narrowband. What is the basically advantage of broadband? Collect radiation across a broader range of lambda per band or this wavelength. So, more photons and more energy, and that is why broader bands are used. In case of thermal infrared also, the emission in order to register that value you require broadband. So, in thermal infrared narrow bands are not possible, and narrow bands give more spectral details, however less energy available to be registered. So, lower signal or lower signal to noise, and more bands, more information to store, transmit and process. So, if application really required, then one should go for multispectral or hyperspectral. Remember, but when you go for such a kind of options, then the footprint or the swath will reduce, area of coverage will reduce, and but more bands enables discrimination of more spectral details. So, if somebody is working for mineral exploration, trying to identify some mineral deposits, then always in comparison to panchromatic, your hyperspectral resolution images would be much better. So, there is a always trade off between broadband and narrowband. Everyone is having some advantage. Now, we will also discuss little bit about temporal resolution, and that is the time between observations or repeativity or revisit time over same area of a satellite. Radiometric resolution we have already discussed. When we go for 24 bits, this is 16.7 million colors, 8 bits 256, and likewise you get this example we have seen from radiometric resolution. And just in the last slide of this discussion, I am comparing two CARTO sets. The resolution in one is 2.5 meter, another one is 0.8 meter. So, now from meter we are going to basically centimeter. Sensor type in both the cases is panchromatic, collection time is different, the local time, this is always in local time, and see the swath. It is when you are having 2.5 meter swath is 30 kilometer, and when you are having when you are having a spatial resolution 0.8, that is 80 centimeter, the swath width reduces to just 9.6. So, higher the spatial resolution, less the swath, less the temporal resolution. For only that purpose I wanted to. So, though the revisit here is shown like this, but because of here you are having the camera which are acquiring data in forward direction and backward direction. That is why say 4A and FTA is also there. Orbit per day, there is 14, either 4 or 5 orbit per day, but it is different arrangement. Altitude and altitude, the distance from here is 680 and this is 630. So, higher spectral resolution, higher spatial resolution means narrow swath, this you have to remember, and repeativity may be different in that case. So, this brings to the end of this discussion. Thank you very much.